So it's about 10 past now, so I'll introduce our speaker for today, who's Janosz Dewberry, who's a new postdoc here at CITA. He completed his PhD at Cambridge previously, and he's an expert in accretion disk dynamics and various topics in numerical hydrodynamics and magnetohydrodynamics, and has also touched on other dynamics topics and things like waves inside stars and planets, and waves in Saturn's rings. Yeah, Janosz, if you want to take it away. And yeah, feel free to ask questions in the chat as usual throughout, and I'll help moderate that for you.
Okay. Let me just share my screen here. Can everybody see that and hear me okay? Okay. Yeah, so thank you, Fergus, for that introduction, and thank you all for being here. I've been excited to move here and get to know some of you, at least gradually. Yeah, as Fergus mentioned, I have a number of interests in a variety of topics, but today I'll be talking about some research that I did primarily during my PhD, looking at potential explanations for high frequency variability that's observed in black hole X-ray binary systems, and also in some other cases of black hole accretion. This is work that I completed mostly with my supervisors at Cambridge, Henrik Latter and Gorgon Ogilvy, our collaborator in France, Sébastien Fremont, and also more recently a collaborator in China, Jiaxin Jiang, with whom I'm looking at making some closer comparisons with observations. So this work is mostly motivated by observations of binary systems that are thought from mass constraints to contain an accreting black hole, somewhat like the artist's illustration here. But there's actually more recently been some observations of very similar phenomena in both AGN and following tidal disruption events. So there's potential applications of the theory that I'll be describing today to some other systems, which could be quite interesting to see in the future. We'll start with some observational background just on black hole X-ray binaries. I will be focusing on that application today. For anyone who's not familiar, these are somewhat similar to dwarf novae in that they periodically go into outbursts. So every once in a while, these systems will become very bright in X-rays from accretion onto a black hole. And this outburst will last for periods of weeks to months and sometimes years in some cases. The emission during these outbursts can usually be broken into two main spectral components, a thermal or blackbody component that looks a lot like a classical model of a geometrically thin accretion disk, and a non-thermal emission component at higher energies that's usually modeled with power law and is attributed to a corona of much hotter plasma. These two emission components trade dominance during the evolution of the outbursts in these systems, and this can be tracked to some extent by looking at both the luminosity and the hardness of the source. So the hardness is just the ratio of the photon counts at high energies to low energies. And so if you plot these two quantities for one of these systems during outbursts, you get something like the hysteresis loops that are shown on these plots. So the systems will start out in quiescence, down where they're very dim and the spectrum is very hard. As they begin to brighten, they'll go through what's frequently called a low hard state, in which the luminosity is still relatively low and the spectrum is still quite hard. As they get brighter and brighter, eventually the spectrum will begin to soften, and they transfer over through several intermediate states. Yeah. Sorry? Did somebody say something or no? So they'll transition to what's frequently called a high soft state. And in the high soft state, the emission is almost entirely dominated by a thermal emission component. And it's fairly widely agreed that in this case, the accretion flow is well modeled by very classical models of a geometrically thin accretion disk. The nature of the accretion flow is much less certain throughout other phases of the outburst in these systems, though, especially in the intermediate states, where frequently you have very strong contributions from both the thermal disk component and the power law emission component. And in particular, there are some states in which the flux is very high, in which we see some very interesting rapid variability. So you can see that by looking at the power spectral density. This tracks the power in a given frequency of oscillation. This is a PSD for a particularly interesting source that shows somewhat canonical examples of what's called a low frequency quasi-periodic oscillation. So it's this peak at around 18 hertz. And then this source also shows two high frequency or HFQPOs. And so I focused mainly on explanation for these HFQPOs, and that's what I'll be talking about today. So HFQPOs are quite interesting theoretically, mainly because of their frequencies. So their frequencies are roughly in line with what you'd expect to associate with the orbital motion close to a black hole in this mass range. And the frequencies are also relatively insensitive to somewhat sizable changes in luminosity. So this suggests that whatever dynamical phenomena gives rise to HFQPOs in the disk, their frequencies may be set by the intrinsic properties of the central black hole. So in the case of astrophysical black holes, that means its mass and its spin angular momentum. So here I've plotted the frequencies for several HFQPO observations as a function of independently measured mass on the left and a dimensionless spin angular momentum parameter on the right. And you can see that the error bars on many of these measurements of mass and spin are quite bad. So the hope is that a robust model for HFQPOs would give some better constraints on both of these properties. Unfortunately, this is quite a messy problem, at least in part due to the uncertainty related to...
Can I interrupt just a sec, Janosz?
Yeah.
Go back to the previous slide. So you've got 4 measurements there of GRO J165. Is that at different times, or you get 4 different peaks?
So these are at different times. I think GRO J1655 is the only source that has shown 2 simultaneous HFQPOs. A lot of them do show two HFQPOs at 2 frequencies that may or may not be close to an integer ratio, but most of them are seen at different times and often in slightly different energy bands.
Do you see the HFQPOs in the hard state or the soft state?
In the intermediate state. So the frequently called a steep power loss state. It's a anomalously bright state right before the high soft state.
How's the spin parameter measured in all these cases?
Sorry?
How is the spin parameter measured?
The spin parameter essentially increases the characteristic orbital frequencies close to the black hole.
But the question is, how do they estimate the spin parameter?
Various methods. I think the 2 main methods that are used today are to look at trying to constrain where the inner edge of the disk is, so the innermost stable circular orbit. And the other way is to look at reverberation, so the reflection of emission from the corona that bounces off the accretion disk. And there are some lags, and that gives you a method other than just fitting the emission to get a constraint on the location of the ISCO. Okay. Yeah, so during this very high SBL state, it's somewhat uncertain what the accretion flow actually looks like. Hopefully, a lot of the more recent radiation MHD simulations that could self-consistently generate a disk and a corona might give some more insight in the near future. But so far, because of this uncertainty, there's a lot of degeneracy between the models that have been offered to explain HFQPOs. So these range from very simplistic models that essentially just appeal to particle dynamics, saying there's some kind of resonances between orbiting fluid blobs, to more sophisticated models that look at oscillating torus or thick accretion flow, to the model that I'll be talking about today, which suggests that HFQPOs can be associated with waves that are excited and trapped by relativistic effects in the inner regions of a disk that is thin-ish or slim, surrounded by a corona of some uncertain geometry, and threaded by magnetic fields with potentially some coherent or mean field, as well as a fluctuating turbulent magnetic field as well. So I'll give some theoretical background now. Hopefully anyone who's familiar with this area will bear with me. Before talking about the relativistic effects that could lead to trapped waves, or diskoseismic modes as they're sometimes called, it's worth taking stock of the different types of waves we'd expect to find in an accretion disk. So in a disk that's supported radially by rotation and vertically by pressure, we'd expect rotation to produce a Coriolis force, which can support inertial waves. Since we have a compressible gas, we'd expect acoustic waves and sound waves to propagate in this disk. If there's any stable stratification, we'd expect buoyancy to produce gravity waves. And magnetic tension and magnetic pressure from any coherent magnetic fields in the disk will produce Alfvén and magnetohydrodynamic waves. And all of these restoring forces can work together to produce oscillations with a mixed physical character. To begin to understand how these different types of waves might actually propagate in a disk, we can look at pretty much the only equation that I'll reference in this talk. So if you consider just a differentially rotating barotropic geometrically thin disk and introduce some plane wave perturbations with this exponential form, you can derive a dispersion relation that's something like what I've written in this white box here. So Kr, M, and Kz are all just radial azimuthal and vertical wave numbers in a cylindrical coordinate system. Omega is the frequency in the inertial frame. Cs is the sound speed. And then kappa and omega z are the horizontal and vertical epicyclic frequencies of oscillation. These are the frequencies that a particle or fluid element on a circular orbit will oscillate either radially or vertically if they're perturbed from that circular orbit. In a Keplerian disk, these characteristic frequencies are both equal to the orbital frequency omega, but this is not true in general, which is the main reason I'm able to have this talk today. Returning to this dispersion relation, you can see that kappa and by proxy omega z do a lot to determine the regions in which we'd expect different waves to propagate in an accretion disk. So for an oscillatory solution with a wave-like behavior, we need Kr to be real. So that means that the right-hand side of this equation needs to be positive. And that gives several different types of waves. I'll mention a few of them. So the simplest types of waves with Kz equals 0, so no vertical structure with respect to the midplane, are governed by the very classical spiral density wave dispersion relation. I'll refer to these waves as inertial-acoustic oscillations or waves throughout the talk. On the other hand, if we have some waves that have vertical structure, so wiggles with respect to the midplane, then there's a few families of waves. There are acoustic waves that have higher frequencies and can propagate wherever the square of this omega hat is essentially the frequency in the rotating frame, except should keep in mind that this is a spatially variable quantity. So wherever this omega hat squared is greater than some integer multiple of omega z squared. And alternatively, you can have lower frequency inertial waves that are governed by this constraint here. So we can represent these restrictions on wave propagation visually with a wave propagation diagram. So this shows that the shaded regions in this plot show that the radii that waves of a given frequency are allowed to propagate. So in a Keplerian disk, the axisymmetric inertial waves that I mentioned on the previous slide can only propagate where their frequencies are less than the local orbital frequency, and vice versa for acoustic waves. You'll notice that in this case of a Keplerian disk, because the characteristic frequencies are both equal to the orbital frequency and they're all monotonically decreasing, the wave propagation is quite boring. We don't expect to have preferred radial location or any discrete frequencies for these waves. That changes close to a black hole, where relativistic effects will cause both kappa and omega z to differ from the orbital frequency. So in particular, close to a black hole, the square of the horizontal epicyclic frequency kappa falls below 0. This defines the innermost stable circular orbit, or the ISCO. And it also produces a maximum in this case around 6 gravitational radii. Here Rg is just a dimensionless spatial unit. It's half a Schwarzschild radius. And it's this non-monotonic variation in kappa, this maximum, that produces a lot of the interesting possibilities for exotic wave propagation in a relativistic disk. Can see that by, again, considering the very simplest waves with no vertical structure. So kz equals 0 is inertial acoustic waves. And if we think about axially symmetric modes, so m equals 0, no spiral structure, you could have an inertial acoustic wave that is trapped between this profile for kappa and the inner edge of the disk, assuming that it is reflected there. Alternatively, the presence of the ISCO itself and presumably a transonic inflow through the ISCO can give rise to some viscously overstable inertial acoustic waves with higher frequencies. The plot on the right here shows a snapshot of surface density from a simulation in which this transonic inflow has excited a viscously overstable inertial acoustic mode. There's also quite an interesting instability that can excite non-axisymmetric inertial acoustic waves, or F modes. In this case, you can again have waves that are trapped in the inner regions of the disk, assuming that they are reflected at the inner boundary. And a transfer of wave energy across a co-rotation resonance, this is where the pattern speed matches the orbital frequency in the disk, can lead to fairly virulent growth of these oscillations. Again, assuming that there is wave reflection at the ISCO. So the snapshot on the right here shows an m equals 3 F mode that's growing in a simulation I ran where I just imposed a rigid wall at the ISCO. However, in a black hole accretion disk, we certainly don't expect to have perfect reflection at the inner boundary. So ideally, we'd like to appeal to oscillations that don't rely on this kind of reflection to produce a discrete trapped wave. There are some possibilities for this if you consider waves that do have some vertical structure. So if we think again about the inertial waves, axisymmetric inertial waves are restricted to propagate where square their frequency is less than kappa squared. So that means that you could have some waves that are trapped beneath the maximum in kappa, somewhat in analogy to how gravity waves can be trapped by the peaks in the Brunt-Väisälä frequency in stars. So the plot on the right here just shows a vertical slice. This is the radial mass flux perturbation associated with one of these oscillations. You can also have trapped inertial waves that are non-axisymmetric, but these are thoroughly disfavored as a model for HFQPOs because most of them are actually fairly strongly damped at their co-rotation radius. You can have some trapped waves that don't have this co-rotation radius within their trapping region, but these have, in general, frequencies that are somewhat too large to explain HFQPOs. Lastly, there is another family of modes that could provide a potential explanation for HFQPOs in systems with very large spin angular momentum parameters, so near maximal spin. In this case, you can get some corrugation modes with much lower frequencies that can be trapped in the inner regions due to the difference between the orbital frequency and the vertical epicyclic frequency. In this case, the fundamental corrugation mode with the simplest vertical structure and just m equals 1 basically corresponds to the lens-Thirring precession of the disk.
Janosz, can you just remind us quickly, in these units, omega over omega g, where are the HQPOs seen, high frequency QPOs?
So it depends on the spin angular momentum, but sorry, it depends on the mass. These are frequencies essentially scaled by mass.
Yeah, exactly.
For a 10 solar mass black hole, I think 0.035 corresponds to 100, a few hundred hertz. So 0.1, 0.2 is much too large. That's in kilohertz for this mass range. Just get some water.
Since we're stopped, can I ask a question?
Yep.
This is Eric here. So I'm curious, you haven't said much about how you do this calculation. So are you in full GR with a full relativistic model for the disk?
No. So I'm actually focusing on the magnetohydrodynamics. So I have used essentially pseudo-relativistic treatment where you use Newtonian hydrodynamics or MHD, but you replace the frequencies, these characteristic orbital frequencies, with their fully relativistic versions. This is not quite accurate, but it has been shown to produce fairly similar results to a fully relativistic treatment.
Okay, thank you.
Yeah, so, and in general, most of the work that I've done looks at qualitative behavior of these oscillations in response to the dynamics in the flow. So the frequencies themselves shouldn't be taken at face value, but the way they scale is what's interesting here. So I've focused mostly on the propagation and properties of the trapped inertial waves. So these modes that are somewhat mathematically analogous to trapped gravity waves in stars. These are a nice family of modes to consider, at least in hydrodynamic models, because they're, first of all, their frequencies are roughly in line with observations. So, excuse me. This surface plot shows possible values for the maximum in kappa, which in a purely hydrodynamic model provides a bounding frequency for these trapped inertial modes. So these are broadly consistent with observations. One thing that is clear from this plot and from other stuff I'll show you later is that these trapped inertial modes cannot provide an explanation for all of the observations. And we certainly wouldn't expect them to provide, I keep losing my mouse there, explanation for systems in which we observe two simultaneous HFQPOs. So if you appeal to a diskoseismic model for these phenomena, then you're certainly going to need some nonlinear interactions between different trapped waves, and that's something I'll discuss later on.
Is the upper and lower bounds caused by the different spin parameters on the left-hand panel?
Yeah, so I'll later on, I've included a surface here. This variation is due to potential different spin values, and this is due to different potential mass values. I put the surfaces on here because the constraints on both the mass and spin are so bad that scaling them for a lot of these observations doesn't quite work. But I will return to that later on. Yeah.
Can you infer from this plot the frequencies are higher or lower than the maximum epicyclic frequency?
Not from this plot. So if we scale the frequencies by mass, then you can make a more direct comparison, and I'll do that later on.
Okay.
A large part of my work has focused on the effects of magnetic fields and MHD turbulence on these oscillations. So if you include some coherent or mean magnetic fields in your model of a disk, then you can derive a much more complicated dispersion relation than the one that I showed you before that suggests that the inclusion of a poloidal magnetic field threading the disk vertically alters the trapping of these oscillations. So essentially a vertical magnetic field in the disk applies an additional restoring force from magnetic tension. And in some cases, depending on both the distribution of this of the vertical magnetic flux and the strength of the field, this can do away with the non-monotonic variation in kappa that gave us a wave propagation cavity in the first place. So this wave propagation diagram is one in which I've included a restoring force from just a purely homogeneous vertical field. And in this case, the field is strong enough that it pushes the trapping region right up against the edge of the ISCO. So we no longer have this favorable possibility for a trapped wave. However, this effect on the trapping, as I mentioned, depends on the strength of the field, but also the spatial distribution. So the vertical field isn't destroying the oscillations, it's changing their physical character to make them Alvanic epicyclic waves instead of just purely inertial waves. And the converse effect of having magnetic fields affect the oscillations is that the oscillations affect the magnetic fields. So this shows a somewhat exaggerated distortion of the vertical magnetic field due to one of these inherently MHD oscillations. And this effect on magnetic fields could provide an important connection between oscillations in a disk and the fact that HFQPOs are primarily observed in slightly higher energy bands, so in the non-thermal emission. And so potential mechanism for imparting variability from disk oscillations to a corona is if you have magnetic fields threading both, then the way MHD waves in the disk could produce some variable signature in the coronal plasma. One other thing I'll mention is that if you additionally include a very strong toroidal magnetic field component, which we would certainly expect to be generated by magnetorotational instability in a disk that's started by vertical fields, this toroidal magnetic field component tends to reduce the effect of a vertical magnetic field on the oscillation. So magnetic pressure associated with a very strong toroidal magnetic field inflates the pressure response of the oscillation. And in doing this, it increases the plasma beta, that's the effective plasma beta associated with the vertical field, and reduces this effect of the tension restoring force that I mentioned before. So you can see in this case with a very strong toroidal magnetic field and the same strength of vertical field, it's started to push the trapping cavity away from the inner edge of the disk. Regardless of the effects of coherent magnetic fields on trapped inertial waves, any diskoseismic oscillation is going to need a robust excitation mechanism to pump them up to large enough amplitudes to explain the luminosity variations that we see as HFQPOs. So I mentioned that inertial-acoustic waves can be excited by a co-rotational instability or by viscous overstability. On the other hand, these trapped inertial waves are very likely damped by MHD turbulence and also by a resonance at co-rotation. So they need an alternative excitation mechanism to be a viable explanation. Excuse me. And it turns out that these trapped inertial waves can be excited by a nonlinear interaction with a distortion in the flow. So either a warp or an eccentricity. So a non-axisymmetric warp or eccentricity essentially facilitates an interaction between the axisymmetric trapped inertial wave, or R mode, that we might want to associate with the HFQPOs, and an intermediate non-axisymmetric inertial wave that is propagating within its co-rotation radius and can be seen as carrying negative wave energy. So this interaction allows the two waves to draw energy out of the differential rotation in the disk and for both of them to grow in amplitude over time. So what I've been doing over the last year or two is looking at whether or not this excitation mechanism might be capable of overcoming damping of these oscillations by MHD turbulence. And so I've been coming at this with simulations. It is fairly well accepted that we would expect many accretion flows in these black hole X-ray binaries to be warped. So whenever there's a misalignment between the bulk angular momentum of the disk and the spin angular momentum of the black hole, the inner regions of the disk can become warped as shown in this simulation. Unfortunately, warped accretion disks are very expensive to simulate. So I've been looking primarily at potential excitation of various waves by eccentricities in accretion disks. There's lots of mechanisms for exciting eccentricities in accretion disks. The one that is relevant for black hole X-ray binaries is a tidal interaction with the companion star. So at a radius in the disk where the orbital frequency of the disk is 3 times the orbital frequency of the binary, there's a instability that excites eccentric distortions, which can then propagate inward through the disk towards the innermost stable circular orbit. So here I'm plotting some eccentric disk solutions. This is component of the complex eccentricity, 4 different mass accretion rates. And the thing to notice here is that for larger mass accretion, the eccentric distortion reaches the inner boundary with a larger amplitude. So this could provide a potential differentiating factor that would explain why we only see HFQPOs in these very high states in which the flux is very high.
Sorry, I'm really lost here. What do you mean
sorry.
eccentricity propagate into the?
So if you excite the eccentric distortion, that it propagates basically like a traveling, but in axial symmetry, stationary wave inward. I'll show some videos later on that show this propagation.
And how does it have to do with high state, low state?
So what this plot is showing is eccentric disk solutions, 4 different mass accretion rates. And so for a larger mass accretion rate, the eccentricity, this is assuming some parameterized damping of the inward propagation of the eccentricity, which is actually a fairly, it's not well understood how MHD turbulence might damp eccentric distortions. But assuming that there is some damping of this eccentric distortion, for a larger mass accretion rate, this inward propagation allows the eccentric wave can reach the inner boundary with a larger amplitude for larger m dot. Does that make sense?
Okay, so the eccentric wave propagates inward, but they don't have problem with streamline crossing?
That's actually something I'll come to a little bit later, but that depends on the spatial variation of the eccentric wave and the amount that it's twisted. There are conditions for orbital intersection. In a fluid disk, we expect strong pressure effects to keep this orbital intersection from occurring. But in general, I think in most binary systems with low, so in superhump systems, for example, usually the eccentricity that's generated is around 0.2 to 0.3, which certainly with this wavelength for an eccentric distortion wouldn't produce orbital intersection. So you notice because this is a log scale, these are actually very long wavelength disturbances. So that it's fairly mild distortion of the flow.
So can I, since you mentioned super humps, which you see in CVs, of course.
Yeah.
Do you see them in these black hole candidate systems?
They do observe some super humps in some systems. I believe the observations are complicated by a potential for disk self-irradiation.
Okay, and are they the ones that show the high frequency QPOs and not in the ones that don't? Or is there any relation between the two?
I am not aware of any relation between the two. So I have not seen any observational studies that actually give any kind of estimate for eccentricity, even in systems where they do see these super humps. So I think it's somewhat difficult. It's more difficult than in the super hump systems to infer an actual eccentricity in the flow.
Janosz, sorry, I also have a question.
No, please.
It looks like the main difference between these different solutions is the accretion rate.
Mm-hmm.
Is that because the higher the accretion rate, the more viscous heating you have and the fluffier your disk, so the faster eccentric disturbances can propagate?
Yeah. So these calculations I did following a method that Barbara Ferrer and Gordon Ogilvie did a few years ago. And their explanation for why a larger mass accretion rate allows the eccentric distortions to propagate inward with larger amplitudes is that this increases the disk thickness to some extent, and the propagation speed is somewhat larger as they reach the inner disk with a larger amplitude. Right, so last thing here is because these are inward propagating waves, it's not a wave that's necessarily reflected to form a standing mode. They form twisted disk solutions. So there's a radially varying phase in the distortion. So we have semi-major ellipses that are misaligned with respect to one another. Here I've plotted the streamlines that correspond to one of these this cyan colored curve. So I've been putting similar twisted eccentric structures into both hydro.
Before you move on, I have a question.
Yep.
Can you go back? Yeah, so coming back to Yanshin's comment, if the eccentricity gradients are large enough that the orbits intersect, does it mean that you get, my intuition tells me that you should get shock waves. Is this what you see in simulations?
Yeah, in simulations in which I force very large eccentricities, I do see shock formations.
I see.
I focus on simulations in which I don't force them so strongly that you get shocks, but we do get very strong compression.
What determines the eccentricity at the wavelengths of these eccentric waves? Is it just by the binary companion, which gives a particular wavelength? Or?
No, it's the structure of the disk. Both the effect of the gravity.
But there can be any wavelengths. If the companion only gives about a boundary condition, there can be any wavelengths, eccentric waves?
So you can have eccentric waves with different wavelengths. It depends to some extent on the potential of the central object also. So in a relativistic disk, because of this difference between the characteristic frequencies that I talked about earlier, the wavelength actually shortens very close to the ISCO. And that'll be relevant later on. So in most cases, you'd expect wavelengths to be very, very long compared to the scale height in the disk, but very close to the ISCO, it becomes much shorter. And that's basically because of the potential of the central object.
Because I guess my question was, if there are short wavelengths, waves also excited, they would streamline cross and damp away the eccentricity before this, before you actually propagate all the way to the ISCO. So the fact that you have a gentle eccentricity gradient is helpful for you to go all the way in.
Yeah.
But is that the only wave that's available? Is there any other thing that's damping the eccentricity gradient?
That's a very interesting question that I'm working on more generally. Yeah, the understanding of how and to what extent eccentricities are damped is not well understood, at least as far as I know. The fact that they are long wavelength disturbances in a lot of cases is appealed to as an explanation for why they might not be damped. They should be long lived, but they are also inherently unstable. So in addition to the excitation of these trapped waves, they also produce wave turbulence due to exciting small scale inertial waves. And this provides it's a parametric instability. So they dump energy into small scale inertial waves that break and form wave turbulence that draws energy out of the eccentricity. So yeah, that's a good question. It's not been well constrained how much you'd expect these eccentric distortions to damp.
Could I just ask two quick questions? One is, I assume that these eccentricity waves are the same as the waves you've been talking about before, except they're m equals 1 and they're a much lower pattern speed. Is that correct?
Yeah, they're in the low frequency regime.
I guess the second question is, I know that many years ago, Hank Sprout was trying to think about such waves in the context of providing accretion in cataclysmic variables. And I think what he always found was that the amplitude of the waves tended to decay as you went inwards for reasonable distributions of the parameters of the accretion disk. So could you say a little more about, based on conservation of action, how the amplitude is changing as you go inwards and what the difference is between, what's ensuring, what you need to get the amplitudes to stay high as you go
So I haven't heard about transport from eccentric distortions discussed before. Is this, are these low frequency non-axisymmetric waves that he was discussing? Or?
Yes.
Okay. Oh, that's interesting. No, that's not something I'm familiar with. My understanding, at least so far, is that the inward propagation is dominated by, and certainly with simulations and with calculations, is that the inward propagation is dominated by any kind of damping and well, in this case, the mass accretion rate. But there is also there are some nonlinear steepening effects that have been looked into that I do observe in these simulations, and that's something I'll come back to in a bit. I'm not incredibly versed in the theory behind how those work, but
the action wave action conservation is a good way of thinking about it.
Yeah, I mean that's not something I've considered in great detail. Right, so I've been looking at both hydrodynamic and MHD simulations in which I throw in distorted disks like the one shown here. So the color plot here just shows radial velocity, and I've superimposed streamlines that are forced to be distorted by an outer boundary condition that I'm imposing. So it's again too expensive to simulate the full radial extent of the disk. So I've truncated the disk some distance away from the innermost stable circular orbit. Here I'm just using a Pachinski-Wida potential to simulate relativistic effects. And I've imposed a precessing non-axisymmetric density profile. And so this basically produces a pressure gradient that forces the inward propagation of these waves. So this is an unfolded polar plot. So the circular streamlines would be straight up and down. So this shows the distortion in the flow. The bottom plot here just shows an estimate of the eccentricities variation with radius. And yeah, we find that there is this nonlinear steepening of the waves that produces a decrease in the eccentricity amplitude very close to the ISCO.
Sorry,
yeah.
I know you've been hounded by questions, but what are the boundary conditions that you're using for these simulations?
Yeah, so at the outer boundary, it's basically a rigid condition, but I have this forcing condition on the density. So I'm enforcing Keplerian rotation except for imposing this density profile. On the inner boundary, I'm just using outflow boundary conditions. So a diode condition, anything that's going in through the inner boundary is allowed to pass through, but I don't allow material to enter the domain. Vertically is an interesting question, actually. So these simulations I've run are unstratified. So I don't include the vertical component of gravity. That's for numerical expense. This is basically focusing on the midplane of the disk. And this has introduced a lot of numerical issues that I would certainly like to sort out with more expensive, fully 3D simulations. Because some of the oscillations that are excited produce some, we believe, numerically spurious structures that formed. I've looked at simulations that both have periodic vertical boundary conditions and in which I've imposed a rigid lid. So this just, because the eccentric distortions we're putting in these unstratified simulations don't have the eccentric breathing, the only thing this really affects is how the waves that the eccentricity excites behaves. And it just causes them to form standing modes instead of vertically traveling waves. Does that answer your question? Okay. Yeah, so putting these distorted disks into 3D hydrodynamic simulations, we do get a fairly clear excitation of trapped waves. So these are space-time diagrams that show radial mass flux in some hydrodynamic simulations. And in this case, you can see that for larger and larger, but still very modest values of eccentricity, they're quite small again because of this nonlinear steepening of the eccentric waves. There's some excitation of clearly periodic behavior. In this case, right around the expected trapping region for these trapped inertial waves, which is around 8 gravitational radii. Can diagnose the oscillations more clearly by looking at power spectral density. So this plot shows power spectral density as a function of both radius and frequency. It's basically a simulation generated version of the wave propagation diagrams from earlier. And there's a fairly clear peak close to the maximum in kappa. Here the dashed line shows the profile for kappa, just assuming particle orbits, whereas the dotted line is actually calculated from the flow, because the pressure gradient in the disk can alter the horizontal epicyclic frequency. An additional feature that we found in these, by looking at these power spectral densities, is some nonlinear excitation of outwardly propagating inertial acoustic waves. So you can actually see these on these space-time diagrams as these diagonally slanted lines. You get some outwardly propagating, essentially density waves. You can see that also by looking at this video. This is azimuthally averaged radial mass flux. It's a vertical slice in the disk. And so the azimuthal average takes out the eccentricity, and all we see is the modes that are excited. It's letting that run. There's some, giving it an initial kick, and eventually we get the formation of these semi-coherent standing wave patterns. And as this excitation mechanism saturates, there's some outwardly propagating vertically homogeneous density waves. But accretion disks are certainly not hydrodynamic. And the more interesting question is whether or not this excitation mechanism can work in a more, at least somewhat more realistic disk in which we have MHD turbulence that's driven by the magnetorotational instability. So to look at this, I've run similar simulations in which I force eccentric distortion. This time I've forced eccentricity into simulations that have been pre-saturated with MRI turbulence. So I've used a fairly vanilla simulation setup with a zero net flux through the simulation domain. So it's fairly mild MRI turbulence. And imposing this forcing boundary condition, we again get distorted disks. This sequence of unfolded polar plots just shows stronger and stronger distortions in several of these simulations that were all initialized from the same MHD turbulent state. In this case, the picture is quite a bit messier, but it does look like sufficiently strong eccentric distortion can excite trapped waves of one character or another. These space-time diagrams again show various averages of the radial mass flux. The top plot is from circular unforced disk simulation, so there's no forcing boundary condition here. And there's no very clear periodic signatures. In simulations in which I do force eccentricity, somewhat larger than in the hydrodynamic case, but still fairly modest, there's clearly an enhanced periodicity in the flow. And if we take a vertical average that corresponds to the vertical structure of at least some of these trapped inertial waves, there's some signatures that appear at least somewhat similar to the trapped waves that we saw earlier. Caveats here are that in the midst of all this other enhanced periodicity, it's not clear that these trapped waves would actually produce something observable. And again, as I mentioned, the MHD turbulence in these simulations is quite mild. So I think it would be interesting to come back with fully stratified radiation MHD simulations to look at this. One last thing I'll say about the oscillations excited in these MHD simulations is that they do show a frequency enhancement due to the mean magnetic field. So the solid line here shows the horizontal epicyclic frequency just calculated for particle orbits, whereas the dotted line shows an additional frequency enhancement for the R mode trapping region associated with just a mean magnetic field that I averaged over space and time for these simulations. Or sorry, just over time for these simulations. This is somewhat interesting if we go back to the observations. Yanchin, I mentioned before that I look in some cases or it was a clearer picture if you look at scaled frequencies. So I've only included observations here for which we actually have fairly robust mass constraints. But if we scale the frequencies by mass, then you have a direct comparison between the theory and the observations. So here, the black dashed line shows the maximum in kappa, which provides a bounding frequency for purely hydrodynamic trapped inertial waves. But if you apply a similar increase in frequencies to what we saw in the simulations on the previous slide, then this agrees more with some of the other observations. Again, the trapped modes certainly can't explain all of the observations. I think this source in particular, GRS 1915, is at least some of the HFQPOs are better explained by these corrugation modes or processing warps in the disk. Lastly, I just want to touch on an additional effect that we found in these MHD simulations. So for stronger and stronger eccentricity forcing, we found that past a certain point, the MRI turbulence starts to be weakened. We believe because of this nonlinear steepening of the eccentric waves. So very strong, very short wavelength variations in the eccentricity and also twists in the disk have a few effects. They, first of all, can alter the angular velocity profile, which Scott, I think you looked at back in the 80s, actually. And secondly, they can produce fairly strong compression, which you assume from just looking at the streamlines here, they come very close together. For any stronger distortions than what I put in this OMOG, you do get shocks, as I mentioned before. And so the weakening of the MRI in these simulations may be peculiar to this case of a eccentric wave that's steepening due to shortening wavelength close to the ISCO. But that does beg the question of how eccentric distortions in general affect the evolution of the magnetorotational instability. So that's not something that's been looked at in great detail yet, and it's something that I'm currently quite interested in. This is just a final video from a simulation that was run with a point mass potential, so no relativistic effects. I've again pre-saturated the disk with MRI turbulence, and I've imposed a similar density boundary condition at the outer boundary. The bottom plots here just show vertical slices, whereas the top plots show, I think, mid-plane slices in R and phi. These are just the different MHD variables. So letting this run, I turn on this forcing boundary condition, produces a eccentric distortion with an eccentricity maximum close to the inner boundary here. And you can see that this at first affects and weakens the MRI turbulence. Eventually it picks back up again. The effect that I'm quite interested in is that it seems to generate a quasi-coherent toroidal magnetic field. So there's an enhancement to the mean magnetic field in the regions where this disk is most strongly distorted. So that's an area of current research for me. So I'll finish there. Summarize, HFQPOs present a fairly interesting but still rather murky window into properties of black holes and their accretion flows. One potential explanation for at least some HFQPOs is that they could be related to oscillations in an accretion disk, which can, in the case of trapped inertial waves, be excited by a coupling with eccentricities or warps in the flow. This is certainly not the answer to the full question. I think there's a lot of future work that could be done. most immediately in looking at fully self-consistent radiation MHD simulations of this type of system. There's also, as I mentioned, been some observations of HFQPOs and AGN and TDEs, in which case the properties of the accretion flow are actually somewhat less uncertain. So I think it could be quite interesting to look at trying to explain HFQPOs in those systems. And as I mentioned, I'm quite interested in looking at more fundamental effects of eccentricity on the evolution of the MRI. Thanks. I'm happy to take questions.
Yeah, thanks, Janosz. Super interesting talk. Yeah, and now so we've got kind of the next until 5 o'clock or so. We can keep this open if anyone wants to do some discussion. I think we have that booked, so I'll just open it up for questions. It looks like Chris has one.
I did have a basic question.
Mm-hmm.
The details here depend on the background structure of the disk.
Yeah.
In fact, I was just looking back at the Ferreira and Ogilvy paper
Mm-hmm.
that dealt with the eccentric wave propagation and noticing that the high m dot surface density profile shows a much more marked dip in the center.
Yeah, it did. It did.
Than to the lower m dot solutions. Presumably that's relevant for the amplitude of the mode in the inner disk. But this gets back to the general question. You know, these systems are showing these dramatic state changes.
Yeah.
And that presumably in significant part has to do with changes in the structure of the disk.
Mm-hmm.
So how confident are you that when you're addressing these, the identity of the mode and doing these mode calculations, you have the right disk structure?
Not very confident at all. I mean, I looked at sort of the simplest model possible to suss out the effects of magnetic fields and MHD turbulence. But I certainly think that changes in the disk structure would change the type of oscillations excited. I am quite interested in how these oscillations would change in a disk in which you've carefully taken effects of radiation into account.
I mean, in some sense, given all the uncertainties in the disk modeling,
mm-hmm.
one would ideally like to use these modes as diagnostics. That make a more convincing ID as to what's driving these oscillations, then work backward and say something about what's actually happening to the disk. But I guess we're not there yet, or we're getting there.
Yeah, no, I don't think we're there yet. And unfortunately, I think it would be quite difficult to explain all of the HFQPOs with one model. I think the observations are too distinct for the different systems, so it may be difficult to. I don't know. I'm a little pessimistic with using HFQPO with using this kind of model to constrain mass and spin. I think eventually that would be cool, but we're certainly a long way from that.
The coming and going of the QPOs with the hardness suggests that the corona is playing some role in this. Do you see what the interaction of the corona with the disk oscillations might be?
Yeah, well, as I mentioned, I think the fact that with magnetic fields, these oscillations become inherently MHD waves could be interesting for the fact that we do see the HFQPOs in the somewhat higher energy emission bands. A problem with a lot of HFQPO models is that they're too robust. You'd expect to see, if you were to say that you just have direct luminosity variations from these trapped inertial waves, then you would expect to see them in other states as well. So the high soft state, for instance, not just this intermediate very high state. So I think it would be interesting to look at how having a corona in a model could allow the oscillations to, if they're interacting with this corona to produce an observable signature that you wouldn't see otherwise. But yeah, I think I was just taking part in a conference the other week where all the observers were talking about, I think the determining properties of the corona is really the popular thing to be doing these days, because understanding how that interacts with an accretion disk or how they're tied together is something that will be quite important to understanding how these HFQPOs work.
Scott, are you implying the corona somehow? If there is a corona, then the wave can leak out vertically or something like that?
No, I'm not trying to imply that, although that's certainly possible. But I mean, the idea that the QPOs are associated with disk oscillations is a hypothesis. I mean, it's at least conceivable that it's some phenomenon that's almost entirely restricted to the corona.
Oh.
Yeah.
I see.
I guess one thing I've not been sure of there is whether you'd expect to find the same characteristic frequencies of orbital motion in the corona. If it's a very thick structure, it's not clear to me that you'd have the same relevance of these horizontal and vertical epicyclic frequencies. But yeah, the picture that is attractive, at least in my mind, is that you could have these oscillations in a disk which send Alfvén waves into the corona and cause some time-dependent reconnection or something. And there have been some interesting studies in the solar corona looking at wave-driven reconnection due to waves propagating outward.
And what's the story on QPOs around neutron stars?
They're very different systems. I'm actually, so I mean, Chris has pointed out to me that for higher mass neutron stars, you might expect the surface to come close to or within the ISCO. So I'd be curious if the trapped inertial-acoustic waves, the spiral density waves, might be more relevant there, where you actually have a hard surface to interact with. The observational properties of neutron star QPOs are quite different. So as I mentioned, the HFQPOs and the black hole X-ray binaries don't vary very much with changes in luminosity. So they don't appear very often, but when they do appear, they're fairly stable. I believe neutron star QPOs do vary quite a bit as the luminosity changes. So I think the general consensus is that they're likely due to different effects.
Well, while we're on this subject, I mean, one thing that's popular in black hole studies these days is trapping of magnetic flux inside the ISCO, which may then force an expansion of the inner, in some cases, an expansion of the inner boundary of the orbiting material. And to what extent has that been involved in the latest QPO models for black holes?
I don't think it's been folded into very many models, at least not explicitly. I mean, Dong Lai is the one who's done a lot of work looking at these non-axisymmetric inertial waves, and he certainly appealed to the idea of having a magnetosphere that might provide this reflection for these waves at the inner boundary. But beyond that, I don't think it's talked about a whole lot. Certainly, most of the observational studies just assume that well, no, that's not true. They look at whether or not the disk might reach all the way to the ISCO, but I haven't seen a discussion of whether that might be due to a magnetosphere or to other properties of the accretion flow.
Can I go back to Scott's question in a slightly different way about whether whether you need a disk? I mean, the phenomenology I remember was that you didn't see QPOs in the low state, basically?
Not the
Is
high
that
frequency.
because you can't see them, or because you could see them if they were there, but you don't? Do you have good enough photon counting statistics? Yeah.
I don't know. I mean, the very popular model for the low hard state is a truncated disk model, in which
Exactly. Yeah.
the inner flow is very thick and puffy, and the disk is truncated very far away from the ISCO. And if you don't have a disk to oscillate, then it makes sense that you wouldn't have.
Well, then it would explain that you wouldn't see the oscillations, but it could also be that you don't see them because you don't have enough photons, for example, right?
Yep.
And you're not sure if that's which one it's due to.
No. I mean, to what extent the disk extends all the way to the ISCO during which stages of the outburst is still up for debate. There are some observations looking at, again, this reflection of emission off of the accretion disk from the corona that instead suggests that you do have a disk that extends all the way to the ISCO during most of the outbursts. It's just that the spatial extent of the corona changes instead.
Right, yeah, I've seen that. So that would be consistent within the high state seeing stuff triggered by the disk causing these oscillations, possibly, and as you say, it's in the harder radiation, so probably in the corona rather than from the disk directly. But it'd be nice to know that if you don't have a disk, then you never see QPOs, high frequency QPOs.
Yeah, I mean, certainly the states.
It'd be a big clue.
Yeah, well, in the states where you certainly don't expect, or where I think in the only states in which HFQPOs are observed are states in which you expect to have a disk that extends nearly to the ISCO. Whether or not that's a thin disk or a slim disk or some more complicated structure involving a corona is not clear. But it's not the situations that have been characterized as this truncated disk very far away from the ISCO.
So I have a different question. I have a question about these eccentricity waves. So presumably this is excited by a companion at the 3-to-1 resonances. So companion is continuously extracting angular momentum from the disk and continuously excite these eccentric streamlines at the 3-to-1. That's the starting picture, right?
Yeah, I believe so.
That's for your boundary condition. That's where you set the eccentric streamlines at the outside, and then see how that leads to eccentric wave propagating inward. So in that sense, this eccentric wave is a way of extracting angular momentum from the disk as well.
I suppose so. I'm not
this
sure.
This is not related to QPO.
Yeah,
I'm just curious for binary evolution in general. That how does the companion drive the orbit? How the binary orbits evolve?
Right.
When you have a disk like this.
I'm not sure how efficient that is at actually changing the binary. I mean, especially for it's not there. There's still somewhat mild distortions in the flow.
But it's a continuous forcing at the 3-to-1, right? So when you send the eccentric waves inward, that changes the streamline in such a way that there will be a back reaction on the companion. But it is whenever, as long as it's a companion, it will force eccentricity. So it is a non-stop process.
But I think whatever the accretion process is in the accretion disk, angular momentum is flowing out through the disk. It's got to have a sink somewhere, and the most plausible sink is the companion. So
right.
So
and this is additional, sounds like, right? The 3-to-1 resonance.
Well, if it's a 3-to-1, it will change the relative ratio at which you're pumping.
That's right.
Orbital energy and angular momentum. So it'll have a potentially big effect on the eccentricity.
Right, because the ratio is not correct. Yeah. I have a sort of naive picture that, you're surrounded by a companion.
At least in the case of low mass stars, the angular momentum
Sorry, go ahead, Norm. Yeah.
I was just going to say, at least in the lower mass case, lower mass stars, the companions, the stars initially acts. Yeah, sorry, I got a lousy internet connection. Not sure why. Is it? Yeah, I was going to say the star initially acts as the sink for the angular momentum, but then it, you know, you get rid of it in the stellar wind essentially. Or if you're in a smaller period, which these things aren't, I don't think, then it can be gravitational waves that remove it. So it's not like the star gets pushed away from the disk. It tries to, but it can't do that.
Right, that if the energy and angular momentum are coming in through the resonance, going out through a wind, they're going to go out in different ratios, and so there'll be an effect on the eccentricity.
Absolutely, yeah.
Yeah, so presumably the companion is going to go eccentric as well.
Well, if it does that, usually the tides from the central object then try to recircularize that orbit, right? Because if the orbit of the secondary gets eccentric, then you get tidal damping in that star, which tries to reduce the eccentricity as well, right?
If it's close by, yeah. But for this black hole binary, X-ray binaries,
they're close by because they're overflowing, right? It's Rossi overflow.
Oh, you're thinking about the companion tide. I just find it very. I guess I can't really figure out how to think
that's
about
a question, Janosz. So is this mostly Rossi overflow? Or?
Yeah, it is.
Or are these wind fed?
No, it's Rossi overflow.
They're wind fed or they're Rossi overflow, or both, depending on the system. It's Rossi, yeah, okay.
Yeah, so there are.
So that tells you that tides are going to be really important, right?
Yeah, I mean there are X-ray binaries that are fed by winds, but they're a different class of X-ray binaries.
But is it possible that the entire disk acquires a uniform? I'm not a uniform. Acquires a aligned eccentricity if the angular momentum is taken out. Why does it have to be in the form of inward propagating eccentric waves?
I mean, I think that depends on the structure of the disk. I think in the case that I, or at least in the model calculations that I've done, it's a traveling wave because the eccentricity is damped as it propagates inward. So it's just continually propagating inward rather than forming some normal mode.
Do all these systems show radio jets?
I think many of them do but only during parts of their outbursts. So
I haven't kept track of what's, I know some of them do, but.
So I think the jets are usually observed
in the high.
they're usually observed somewhere to the right of on these intermediate states. So I think the bright hard states, but there's something like it's called a jet line somewhere in here. I'm not sure where. They're only observed above a certain hardness.